A pleasant morning to all of you. The content of this presentation is on physical quantities, standards and units from the chapter Mechanics. I am Dr. Ancemma Joseph, Assistant Professor, Department of Physics, Fatima College, Madurai. The learning outcome expected out of this presentation is, at the end of this presentation, you would have an idea about the physical quantities, standards and units, and the basic units of length, mass and time. And as we think of the term physical quantities, it could be categorized into two types, scalar quantities and vector quantities. And scalar quantity is the one which has got only the magnitude. Say the mass of a substance, it is given as, say for example, 50 grams. We are referring only to the magnitude. The length of a thread, 5 centimeter thread. So I am just referring to the magnitude. The second type is the vector quantity, which has got both magnitude and direction. So if I am referring to the force which I am using it to pull or push an object, say force of 2 Newton. If I am referring it as I am just pulling it upwards, I am including the direction also. If I am pushing it downwards, I am including the direction also. So vector quantity has got both magnitude and direction. So there are so many examples of it. We would see the basic things one by one. So this is just a pictorial representation of what is a scalar versus vector. So scalar has got only the magnitude, whereas vector has got direction. So if I am saying that if I have a vector quantity, it will also have the direction included. So 50 meters east refers to a vector quantity. If I am just saying 50 meters, it is a scalar. So here I am going to define the basic terms of measurement: distance, displacement, speed, velocity and acceleration. When I say distance, it is the measure of the length between 2 points, initial and final points. So distance is equal to the final position minus the initial position. So you can see in the animation that a boy walks from 0 meter point to 6 meter point. Now he returns back from the 6 meter point to the 0 meter. So even though he has walked up and down 6 meter plus 6 meter, the distance covered becomes 0. In order to remove this ambiguity, we go for the second term called displacement, which includes the position also along with the direction. So here it is a vector. I can refer to total displacement as the final position minus the initial position. Here the positions include the direction also. So I will say that he has walked from 0 meter to 6 meter. It is 6 meter right minus 6 meter left. So magnitude wise 0, but direction wise it will give an information about how much he has walked. And if we think of speed, it is the rate of distance with time. So how much distance he has covered with the time. So velocity is the same distance by time with direction include. So it becomes the rate of displacement with time. So the beautiful animation refers like from the boy starts from 0 seconds. So he walks up to 4 meter in 1 second, then another 4 meter in 2 seconds. So we will be able to measure the total distance and the time, and distance by time gives the speed. If I am able to give the direction also, it becomes the displacement. And acceleration is the rate of change of velocity with time. So if the velocity is not constant, if he is speeding up as shown in the animation, or if he is slowing down, so we will be able to get it from the acceleration term. So the scalar and vector quantities pictorial representation we can see here. If I am referring to speed, it is a scalar quantity. Only the distance by time is given miles per hour, 45 miles per hour, whereas velocity is a vector quantity which will also refer to the direction. So it is 45 miles per hour, but he is riding uphill at angle 30 degree. So now we'll come to the second part of the content, measurement of physical quantities. So the measurement of physical quantities involves two steps, the choice of the standard unit and the comparison of the standard to the quantity to be measured. So I have this mass as a physical quantity. How am I going to measure it? So if I'm saying a person is weighing 75 kilograms, what I mean is he is 75 times the unit of mass kilogram. So all measurements are made in physics with respect to standard units, and these standard units are framed by the General Conference of Weights and Measures, and these standard units are called International System of Units, measured or abbreviated as SI units. So for length, the SI unit of length is meter. So in 1983, the General Conference of Weights and Measures redefined meter as, so how do you define 1 meter? It is the length of the path travelled by light in vacuum during a time interval of 1 by this much quantity of a second. So various other metric units are related to meter by either multiples or sub-multiples of 10. So if I am saying 1 kilometer, it is 1000 meter. 1 centimeter, it is 1 by 100 meter. So we have this derived quantities for length. Why do we have all these things? Kilometer, centimeter, millimeter, apart from meters? It all depends upon the quantity which is being measured. Say for example, if I am going to measure the length of a scale, it is not a bigger thing, so I will be using centimeters. But if I am measuring the distance from Madurai to California, I will not be able to do it in meters. So I should be, because it is so large, so I have redefined a derived unit in kilometers. And so for large distances, I would be using kilometers. For wavelength of light in the atomic and microscopic scale, I would be using angstrom unit. 1 angstrom is equal to 10 to the power minus 10 meter. And for nuclear size, I will be using femtometers. So here I have given some examples of the different quantities and their length scales. So nanomaterials 10 power minus 9 meter. So virus, it is 1 micrometer, 10 power minus 6 meters. Hair is in the scale of 100 micrometer. So water molecule, you can see it is 0.1 nanometer. So different examples have been given here. So if I am using astronomical distances, how am I going to measure the distance from Earth to a distant star? So there it would be meaningless if I am measuring it in meters or even in kilometers. So because the distance is so large, so I have redefined a derived unit for it, which I am calling it as light year. So it is the unit of length which is used for astronomical distance measurement. It is equal to the distance travelled by light in 1 year. So 1 light year is equal to 9.46 into 10 to the power 15 meter. And I have a still larger unit called as astronomical unit, AU. It is the mean distance from the center of the earth to the center of the sun, which is equal to 1.495 into 10 to the power 11 meter. So coming to the second basic quantity, the mass. What is the SI unit of it? Kilogram. So the standard kilogram, 1 kilogram is the mass of a particular solid cylinder of platinum iridium alloy kept at the Severus in the international system of units and measurements. So we have again, as in case of length, we have got derived units as kilometer, light year, centimeters. Here if we want to measure very big things, we will be not using kilogram, we will go for 1 ton. We will be using ton. And say for example, if I am going to measure the mass of gold, so So I won't be measuring we won't have it in kilogram measurements, right? For ornaments. I'll be speaking in terms of gram. So milligrams. And for ton is for big mass things. So that is the unit of mass. Now the standard other third quantity is time. So SI unit of time is the second. So 1 second, what is 1 second? It is 1 by 86,400th part of a mean solar day. So what is one solar day? It is the average period between successive transits of the sun across the meridian taken over the 12 months at any part of the earth's surface. So in 1967, the second was further redefined by using an atomic clock which works on energy changes in gaseous cesium atoms. So apart from these three basic quantities, time, length and mass, which are measured with the basic units, SI units, second, meter and kilogram, we have four other basic quantities: the electric current measured by ampere, temperature measured in Kelvin, amount in mole and luminous intensity in candela. So in this short presentation for physics in day-to-day life, we have seen what are all the scalar quantities and vector quantities. We have seen the meaning of the basic and derived quantities and the terms of measurement: distance, displacement, velocity, acceleration, and the SI system of measurement of the 7 basic quantities: time, length, mass, current, temperature, amount and luminous intensity. Thank you.